Welcome to NARI SimCenter's Live Expert Tips. In this session, we introduce you to coupling tsunami or storm surge simulations with local scale structural response. Today's example would demonstrate how to calculate probabilistic response of the structure using tsunami and storm surge simulations. Our expert is Dr. Ajay Harish. Dr. Harish is a lecturer in the Department of Mechanical Aerospace and Civil Engineering at the University of Manchester. He has a decade of experience in the development of numerical methods and algorithms for solid and fluid mechanic problems. Prior to joining the University of Manchester, he was a postdoctoral scholar with the SimCenter at UC Berkeley. Dr. Harish obtained his Ph.D. at the Institute of Continuum Mechanics in Germany, his master's in Aeronautics from Caltech, and he has been the lead developer for the HydroUQ tool, which is aimed at studying coastal hazards. Professor, welcome, and I invite you to begin.
Thanks, man. Thank you very much for the kind introduction. The feeling is still yet to sink in, so that I'm a lecturer now, so it still feels like I was a postdoc in SimCenter, and it was a nice place to be, so I just moved from the nice, warm California to windy, chilly Manchester, so it's still getting adapted there, but thank you very much for joining in today. I'll be talking about the HydroUQ tool, kind of showing about what that is and how it works, and what are the kind of simulations that you would be able to do using the HydroUQ tool. At the end of the day, it's I want to stress here that we are here to help you with these simulations. So it's not okay, hey, here's something, a tool that you can go and use, but we have a very nice support system available through our forum, through these expert tips and various other resources. If you're not looked at the SimCenter website, you should go in and join in, and we are there to handhold you through running these simulations. So if you say, hey, I want to run this simulation, can you help me with it? We'll kind of literally handhold you through them, at least the first couple of them, and then probably once you get used to it, then you'll run them easily by yourself, right? So before I go ahead, I just want to, if somebody might have seen on the LinkedIn, I just want to correct it a little bit here just to set the expectations right. We would not be exploring any data about the Tonga volcano eruption. I saw that there was a post about that. Probably there was some bit of a miscommunication here, but we're definitely not looking at the volcano data, just to make sure that you know what you're expecting, right? So I just want to make the expectations correct here. So we'll be looking at, on the left side, what you're looking at in the picture is some kind of a tsunami simulation that's happening, and on the right side is the high fidelity CFD simulation that resolves a very, very, very small area. So for example, here you can look at that on the left, the small red box on the left side is not even visible. Probably made it visible because I wanted to kind of show it in the presentation, but the area is at this large scale on the left side. The right side area is not even visible. That's why we are kind of calling it as coupling the regional scale with the local scale response. So these are two different length scales. So on one side, you have the huge Pacific Ocean. On the right side, you have one or two small buildings around which you want to look at the local effects on these buildings itself. But then this definitely has nothing to do with the Tonga volcano. I just want to make sure that we're all on the same page there. Just to give you an idea, about the HydroUQ tool. So there are a lot of resources, like I said, you can look at the HydroUQ webpage available there, the documentation, the GitHub page has the code for somebody who wants to go in and look at the code, see how it is working, and probably wants to make some modifications of that. Particularly as researchers, that either you want to use a tool or you want to probably add some of your own module into it and kind of work around with it to see how your models would fare against the standard models that are there available in the literature. So both of these things are possible. Like I said, the SimCenter forum is available there, which is very active and kind of of course HydroUQ tool is a newer tool, so there's slightly less number of posts. But if you look at the earthquake engineering posts like EUQ, COFAM, which have been there for about 5 years now, there's a lot of questions that come in and it's actively answered within like a 12 to 24-hour time frame. 24 hour is like saying like when we are on weekend, probably, give us a little more time, but on a work day, you probably get a response within 12 hours, much earlier than that. But then I'm just giving you like a upper limit in a way by which we respond. So it's not that you are, hey, here's a tool, go use it, but then there's a lot of hand holding there that's available beyond just the manual itself. There's we are there to kind of help you to run these simulations, set it up, and do everything in a way. Right. So I mean, so what is this HydroUQ tool doing? I mean, like I had like some kind of a description in there, but probably pictures speak much better than these descriptions, I would guess. So we want to kind of understand what does this HydroUQ tool does, right? So think of this simple scenario, like on the left side, you can see this red line, which is nothing but some representation of our fault zone or a low pressure zone in storm surges. But since we are looking at tsunamis here, this is our fault zone where there might be an earthquake. For example, this could be the fault zone in Alaska, or like, it could be one in California. And we have a large ocean through which these tsunami waves would propagate. And then we might have like offshore structures like the one in the yellow color in the middle, or there could be a lot of critical infrastructure on the coast as well. Right. Not every building might be of interest. We might not want to model every single house, which might be very difficult to model at that lower length scale. But for example, let's say like in Fukushima, where there was a nuclear reactor, then we might want to take extra care about these kind of critical infrastructure that might be near the coast. And we want to look at like the structural response of these structures. So what HydroUQ does is it gives an universal interpreter that converts your 2D shallow water solutions to a 3D finite element and couples it with couples your 2D shallow water solution with 3D CFD and with 3D finite element and UQ. I don't know any other existing tool in the that exists that would couple all these different technologies. From finite volume with the CFD is done by OpenFOAM, which is a finite volume solver. 3D finite element is done by OpenSees. And then we also have the UQ engine from Dakota. So it gives you a universal interpreter that, hey, here are my 2D shallow water solution. I took a fault zone. I ran some 2D water solution using GeoClaw, for example. And I would like to use this GeoClaw solutions to look at how my building, what is the structural response on my building with much higher fidelity than what GeoClaw provides. What are the forces? How do these buildings deform? What are the structural response? Then essentially that is what HydroUQ does. You can bring in your solution that you have from your shallow water, plug it into HydroUQ, and what HydroUQ does is it automatically takes these things. You can define a region of interest. For example, here I have done that with a small yellow box. Where's my mouse? Yeah, with this small yellow box. So maybe I have right. Okay, I can annotate now. So this small yellow box here, or there's a larger region that I'm looking at here with this larger yellow box here. I have a building of interest, which is the small yellow here, or the one like an offshore structure that is there. And then you can run these CFD simulations that are just looking at the small local scale domain, which would give a really high quality results in there. So essentially, like, okay, run your shallow water solutions, bring these solutions, put them in there into the HydroUQ, set up your domain of interest, saying that, hey, I want to have my domain here. And then automatically HydroUQ takes care of the rest of it to give like a probabilistic response for it. Okay, so, okay. No, so how is, maybe I need to remove the annotation. Okay, clear all drawings. Okay. So what is HydroUQ doing? Some of you might be interested. Okay, 2D shallow waters are like something like a depth averaged velocity. And you're saying that you're going to give me the velocity, right? So I'm basically like saying, hey, here, give me your average number. Let's say you take 1, 2, 3, 4, 5 and make the average of it. And you give me this number, then I'm going to tell you what is your original number, some kind of a magic, right? I mean, in a way. So what is HydroUQ doing here? It's kind of, it kind of does a magic, let's just say. So it's basically taking these kind of average solutions and converting them into a 3D flow field that you can be applied onto the structure, or that can be applied as a boundary condition into your CFD domain to get the structural response. So this again, like we have put up a module here, and I'll go at the end of the presentation, I'll be showing you that this is a researcher module here. So this is an open problem that where you can publish a lot of stuff that if you want to, where there's no perfect solution available here, because here you're, how do you take an average and get the original numbers, right? So I could be thinking of various different numbers, but still I could get the same average in there. So how do I reconstruct these things with minimal information in a way? So that is a challenge in there. So that's where you can also write your own Python modules. That's the open problem out there to look at different models of coupling these shallow water. You don't have to yourself install OpenFOAM, or you don't have to install Dakota or structure or the OpenSees. You just have this small Python thing that can convert into different ways of coupling, and then automatically you can use HydroUQ to do it. So just to show you what's happening here, I would not go into the mathematics of it, but just to give you just a general feeling of the idea. Here, what you have is H is like nothing but the bathymetry, or like the height of the water column. HU is height of the water column into the velocity in the X direction. V is the velocity or the average velocity in the Y direction. And this is what your shallow water is giving. And now basically you can see that in a 2D sense, now you can see that these are basically like points on a line. And now when I look at my 3D domain, or here like the CFD domain, I'm basically converting from one point, I'm extrapolating over the entire line. So I need to somehow have some kind of a some velocity profile that is going to think of it. So there can be two-way coupling. People have tried to do two-way coupling as well between different solvers, even with OpenFOAM itself. But at the moment, we are only offering a one-way coupling. So that's basically an inlet boundary in a way. So your domain should be chosen such that there are no reflections. So once the reflection starts and there's no, let's say your water is coming in, now your waves propagate through your domain. Now waves will reflect back. And once these reflections start to build up, then essentially the results are corrupted. So your domain needs to be small enough or large enough just to avoid these reflections. That's one thing to keep in mind when we are doing this. Second thing, what happens is that once we have these boundary conditions are used to solve the OpenFOAM simulation itself. And then we are calculating the force on each of these floors. And this is directly applied, saved and applied to OpenSees. So there's again a one-way coupling from the fluid to the structure. I mean, one of the rationale here is that the structures might not deform so much. So we are not looking at structures that might get washed away, but more like structures like large evacuation structures or tall evacuation structures that might not get washed away, but might have some force coming in because of these kind of fluid loading in there, right? So the OpenSees would offer a deformed shape in a way, and to understand this deformed shape would not be a probabilistic one, but then kind of not a deterministic one, but a probabilistic one. So you can define your own engineering EDPs, and essentially you would be able to calculate these, like what are the floor accelerations and so on, and what is the distribution of these floor accelerations and things like that. Right. So I'll show you in the HydroUQ as we go into looking at it. I'll show you what happens in there. Right. So this is basically just for somebody who might be interested in the mathematics of what's happening. How are we coupling from the 2D to the 3D? How are we doing the magic? This is just to give you an idea of how the magic is being done. There are a lot of various theories that are out there that can be used, and I'm not saying this is the only way to do it, but then there's one way to do it. There's an open question of like, and always like one can think of different methods to do it. So what we are doing here is we have some water height, and as a reference level, using that we are looking at each of these cells and saying that does this 3D cell have any water in that, or does it not have? So I know the H, which is the height of the water column, and using that I am going to define each of these cells that are there, if there's going to be any water in that, or there's no water in that. Or the problem is when you have a cell where you have, let's say the water is going to be half of it or like quarter of it, then how do we define if it has a water or not? So OpenFOAM has this parameter like an alpha, which is basically saying that what is the volume fraction of water versus air. And that is what we are using here to define for those with without the water or with air is 0, with the water is 1. And ambiguity comes in when there's a cell which is not completely filled, but partially filled. And in this case, we are going to use the volume of fraction to define what is the volume of fraction of the water in this area. So once we are able to define if a cell has the water or not, then comes to reconstructing our 2D velocity with the 3D velocity. So here, essentially, on the left side of this equation, you can see what we have is depending on the height of the water, we are doing some kind of a reconstruction. And very crudely to think about, if you look at this, we are looking at a logarithmic profile. So basically, we are saying that at the floor of the ocean, the velocity of the water is 0, and then we have some form of a logarithmic profile. And using this logarithmic profile, I'm going to fit my 2D solutions onto a 3D curve. Now, is this accurate? Yes, it is not 100% accurate, but as you already understood, we are taking the average and trying to get back the numbers. Like, 1 + 2 + 3 is 6, 6 by 3 is 2, right? I can have 3 other numbers in various combinations to still give me an average of 2, right? So for example, 4, 0, and 2 the average is still 2, but I know that I need 3 numbers. So like, how do I uniquely do it? That's the harder part of it here. That's where the open problem is, where you can probably think about your own modules to put into this aspect here. One thing that we do consider is the conservation of mass. And in order to do the conservation of mass, we take the total mass flux, and we try to make sure that the 2D and the 3D, whatever fluid going into the 3D domain is the same amount of fluid going into what's going out of the 2D domain is the same thing going into the 3D domain. And we kind of scale that in order to make sure that the mass is conserved. Right. So once so this essentially, like I said, so we are taking a logarithmic profile, and how do we calculate various of these parameters, like what's the friction coefficient, 2D friction coefficient, 3D friction coefficient, and things of this nature. So, and this is all available on the HydroUQ website as a documentation page as well that can be directly used. Of course, one can always say, hey, my constant is not this, my constant is something else. Of course, that's where the open problem comes in, like I keep defining again and again. Yeah, so this is something that I want to stress upon here, that the HydroUQ also offers like a researcher. There's also, like, if you look at the user manual, so the user manual, there's a user guide and a researcher guide. So user guide is essentially showing what are the different aspects. So if you open the UI, how does the UI look? Let's say if it says some velocity, what does this velocity mean? If it says pressure, what do you need to input in here? So that's all given into the user guide. But many of you might want to use the researcher guide, where you might want to build something of your own. And you might not want to install everything. I don't want to install OpenSees and Dakota and OpenFOAM and everything, but I just want to write this. I want to study how do you go from the 2D to 3D, right? It's a simple problem. Then we have a Python script available here that you can modify, and you can put it into the HydroUQ to run it. Of course, if you want to run it now, you probably the best way would be to get in touch with us so that we can give you a version that can run it. So not the available. We'll be bringing out a new version soon. The available version doesn't allow you to run this itself, but the feature is already incorporated. So get in touch with us if you want to explore some of these advanced features that are not yet there in the older version. So this is there in the GitHub. So if you go to GitHub and compile the HydroUQ, you should be able to use it, but this is not yet there on the executable that's been released outside. So it is there, but kind of not there. It's like the Schrodinger's cat in a way, kind of. It's right. But yeah, so this is the advanced thing that you can do. So there are a lot. Let me go back to the, can you still see my screen? Okay. Resume share. Oh, okay. Give me 1 second. Let me. So if we go to the researcher guide, I just want to show this, is that so there are various different things. For example, not everybody might use OpenFOAM. You might say, hey, I have my own solver that I would like to use. I don't want to use OpenFOAM, but I would like to still use this coupling between the OpenSees and, with the Dakota. I don't want with the GeoClaw. I just want to replace my own solver in there. there's a small Python script that you can modify. I mean, of course, we would help you to modify this and add things in there that can allow you to bring your own solver instead of OpenFOAM. I would not go into the Waveflume digital twin too much because we already had a session on that. You can go into on the website and have a look at that if you would like. So where you can set up your own Waveflume that can be used. So similarly, the shallow water to CFD interface allows you to, how do you convert from the 2D to 3D? You can write your own Python scripts here that allows you to use the HydroUQ as a researcher tool to expand and explore more topics. And if you go into the user guide, you'll be able to see this, what I said in the user guide. We have like, so when you say event type, so I've marked all the boxes here. So event type selection. So what does it mean by event type selection? So there's a login button that says, okay, login. So where am I logging this into, right? So each of the user guide is pretty extensive and goes into explaining what each of these user buttons are, what are the modules available there, what does it do? Like when I press this button, what happens in there? And if you find something that is not available there, if you think that there's something missing, please let us know through the forum. We would be very happy to add in there and also help you immediately to do that. We try to keep the user manual as much updated as possible, but as the development happens, sometimes these things also fall behind. But we would be very happy to, if you find some deficiency in there, or if you think that you don't understand something, just let us know, and we are more than happy to both help you and also update that into the user manual. We would very much love your feedback so that we can keep it moving and keep it as updated as possible. So we also try to put in some ideas like best practices. One of the things that happens is like some of the inputs into your CFD module can be very difficult to ascertain. Like, so for example, like what's my mesh size? What's a good mesh size? How do I do the temporal discretization? Like what should be my time step size? What should be my boundary condition? For example, here we have the CFD to shallow water to CFD domain sizes, right? So here I'm just giving you an example of, let's say, how do I choose my subdomain? So we had this yellow box in our original picture when we saw previously, we had this ocean and then we have this yellow box. Inside that we have the building of interest, right? So how do I choose this outside yellow box or the domain in order to kind of, let's say, get a reasonable simulation? So when I say, okay, you should not have wave reflection, once the wave reflection starts, then can be complicated. And so how do I calculate these things? So these are kind of some ideas that we have shared out in the best practices. There can be some user errors that you're getting. So if you get an error when you're trying to run it, let us know. We would be very happy to update and also help you with it. We have tried to add in a lot of best practices that we think are useful. But again, we have been using this thing and developing these things, so some things that we think is obvious might not be very obvious to the user. And if you think something is difficult to understand, and let us know. We also have a release note that keep getting updated every time we release a new version. So here we basically talk about what is there in this particular version. So when there's a new version coming out, what are the new changes and new updates that have been made in there and things like that. So bugs and feature requests, again, if you go into our forum, you can see that you can just say you want to release, you found a bug, then please report it to us. Or if you say, hey, I want this new feature, I think this could be fantastic and I would definitely like to use it, please make a feature request in there. That helps us to, streamline the development process. If there's a user asking for something, there's more priority to develop that than we kind of sitting there and, oh, I think the user might like this. I think the user might like a fancy, nice picture coming out of it. Let me put that in there. But then if nobody uses it, it's not really useful, right? I think it's fancy and useful, but then users might not like it. So if you think there is something that you think you would use, you would like, please add it into the forum and we are very happy to add it in there. So there's also an installation manual. So the installation is very simple. If you just go to the HydroUQ download page, so if you go to the HydroUQ, okay, let's go to that page here. Okay, so if you go to SimCenter website, research tools, HydroUQ, so you can see on the left side there, there's like a download app. So if you just press that, then you go into the design save from where you can download all the modules. So there's a DMG file for the Mac. I tried this on the Intel, it was originally developed for the Intel Mac, but I now just was running it on the M1 Mac here now, and it runs on the M1 Mac here. So if somebody is on the latest M1, that should also run. And then you have the Windows version as well that should run on Windows. I don't think they have made any latest changes that would break it so far, at least. So the installation is very simple. Just download it, double click it, and run it, and it should be running there. So, and even for the Windows, you just have to unzip it. There's a HydroUQ.exe, and all you need to do is run this exe file for the thing to run. So there's no real installation or anything as such. You just can download it, and at a click of a button, you can get it to run without having to worry about any dependencies or any installations and so on and so forth. Again, on that, if you go to HydroUQ page, you also can find a link for the documentation here, and also you can find a link. Maybe I should annotate probably. You can find a link for the documentation. You can also find a link for the user forum, so where you can post any questions that you have. You can also post about the if any other ideas that you have that you might want to have it in the tool. Or like if you find a bug, or if you're stuck running a simulation, you say, hey, I'm trying to run this simulation, I don't know how to do it. Can you help us? We are very happy to pitch in and help you with as much as we can, right? So, yeah, so let me just go to the HydroUQ tool itself. Let me unshare this, and I have to share the new window. Okay. So this is what the HydroUQ application looks like. So one of the things is that the HydroUQ runs on design safe. So it does not consume any of your resources or your computing resources itself, but it uses the SimCenter resources. Even if you have an account on design safe, you might have some allocation for the memory and for the resources, but it is not using any of those. It is using only the SimCenter resources in a way. So your compute time is not lost when you run these applications. You're running on our resources there. So once you log in, press the login, you can get a login screen, and you can log in there with your design safe username and account. So there are various things on the left side is where you have all the controls for the different items, and the bottom is basically to run the thing. So for example, exit or get from design safe. Once you're logged in, if you press get from design safe, it's going to give you a list of jobs. And run at design safe is going to run. And run is at the moment, we wanted to have a local run for users to do the testing, but we have not yet incorporated, but that should be available probably in the next couple of versions. We'll try to see that you will be able to run smaller jobs on your local computer if you want to just test it out and things like that, right? But run at design safe is your option. Just put it design safe, everything runs there, and everything comes back in a very nice manner. So I'm not going to some of these things, but I'll just look at the CFD aspect of it. So one is the UQ engine. If you go to COFAM, and if you look at or even if you look at the HydroUQ web page, you have a tutorials on each of these things. My colleagues, Dr. Sangri E, Dr. Akash, Bangalore Satish, Dr. Kwanshi, Zhang have done really a fantastic job. They like went into the detail. They kind of talked about what are each of these options, what it looks like, what they have example files available there as well that you can download and you can test out. So I'll leave them out. So UQ tab is where you can define all the uncertainties. What are uncertainty? Do I want to do a sensitivity analysis? Do I want to reliability, or is just a forward propagation? And like for example, like what kind of methods do I want to use? There's also, I think, something like a neural network as well for somebody who is interested in neural network. I don't remember where it was, but I definitely have seen that. So you can kind of explore there. So general information is just the information about your building that is of interest to you. So we are working here to make it a little more generic. At the moment, it's looking at building, but we also have a couple of users who are looking at bridges and so forth, so on. So we will make this a little more generic in the upcoming version, where you just don't have to think of a building, but you can define other buildings of your own thing like bridges and other complicated structures. So simulation is where you're defining, again, all this simulation, whether you want to do a finite element with OpenSees, or probably you might say, okay, I don't want an OpenSees completely. I'll just think of my building as an MDOF model, and that is sufficient for me to think about it. Then you can also define it that way as well. And I think there's a question, does it work in Linux platform? Unfortunately, I don't think we have a Linux version yet. Yet, but yeah, it works on Windows and Mac at the moment. So, and event is something of the most important thing. Then finite element, you can look at the video by Quanchi on the HydroUQ page. And he has done a great job of explaining what are the OpenSees settings in here that you can use. And EDPs, where you can define your engineering demand parameters, and you can use standard EDPs, or you can also user-defined EDPs. How do you define these user-defined EDPs? Quanchi has done a great job here. Again, what are your random variables? And eventually, once you run your simulation, you should be able to see these results here, and so on and so forth. So most important thing with regard to running these simulations is setting up your event itself. So the event type allows you to choose different simulations. For example, here I am saying I'm looking at a CFD to resolve shallow water simulations, right? So we have done this large shallow water simulation over the entire Pacific Basin, and I want to look at a small building around the California coast. So this is the event I would take in. And once I am there, then I can choose a lot of different things. For example, here it's saying bathymetry. So this is your bathymetry file directly from your GeoClaw. For example, there's a SimCenter format. There's also a GeoClaw format that are supported. And I think in next one, more GeoClaw formats are also supported in the upcoming version. So you can just say, I already have these in the GeoClaw files. I'll just use that. You can just select these files and select the solutions that you have from your shallow water and leave it there. Second thing to define here is the interface file. So how do I define that small yellow box? Right. So if we go back into our documentation, we can see that all you need to do is define 4 points and upload it as a CSV file. So what are the 4 corners of this yellow box? And then from there, automatically HydroUQ is going to look for the points that are inside this domain and which are outside the domain and kind of separate them out. So of course, that means that there might be points that are on the domain. So it considers also these points on the domain within a small error bound in a way that's what HydroUQ is doing. It looks at the distance of the points within this error bound and tries to also look at these points. Last thing is also to define the building. Either you can manually add the building here, or you can also parameterize the building. For example, let's say I want to have a 10 by 10 array. You can just define a 10 by 10 array, and you can say what is the distance between these buildings on the x-axis, on the y-axis, and what is the height of these buildings. You can either choose the building to be either a cube, which is cuboid, which is like basically different length, breadth, and height. Or I can say, hey, I don't want to define a cuboid, I will use user-defined building. In that case, you can upload an STL file. So HydroUQ is automatically going to take this STL file and replicate it to create an array of the buildings. And so this is kind of what is the nice thing about HydroUQ is that you don't have to do all of these manually yourself. HydroUQ is going to do this for you and set up the entire OpenFOAM simulation that can be run in there, right? So other things as like, I'm not going to go into the other things, but because I want to leave some time for discussions as well. If you go back to our HydroUQ page, I keep going back to that. Let me go back to that page. Sorry about that. Okay. If we go back to the HydroUQ page, you can see that we did like a lot of tool training videos here. Most of these are still there because if you find some option that is not there because you took the latest version from the GitHub, then we are happy to help you with it. But then if you're using the installer, all of these versions, all of these things should still be working in there. You can use the navigate, the HydroUQ, and there's also the WaveFlume digital twin that are there. And we also had another expert session, like a session with about WaveFlume itself on earlier in November. All of these would give you various options about the WaveFlume, but then today's about the OpenFOAM. You can just look at the how to navigate HydroUQ. There's a video by Sangri and Akash on the UQ, so both of them have in the same video. Then Quanchi has a video on how do you define the structures, how do you define the EDPs, how do you define finite element and OpenSees parameters. He has some wonderful stuff in there. And other aspects of the HydroUQ last session essentially gives you how to fill in the material parameters, boundary conditions, and so on. So that's kind of where I would leave now, and I would probably we can open up this session for any other questions, I would guess.
Great, thank you, Ajay, for that introduction to HydroUQ and how it couples the shallow water solvers with the 3D CFD solvers. There's a question on swapping out the solver, actually. Instead of GeoClaw, can we use 2D solutions from AdCirc?
Right. So that's an interesting question. At the moment, we are working with some colleagues from UT Arlington to try to get the AdCirc integrated into the solver instead of GeoClaw. If you would be interested in trying to explore that, I would be very happy to help you with it. So there are two parts of the AdCirc, as you might know. One is the AdCirc and one is a Swan. Integrating the AdCirc part is probably the easiest thing. It's probably much easier than the GeoClaw itself, because the way AdCirc saves all the data with a line, with a one Python command, I can get all of these things in there, and I can easily get a new mesh and everything. It's more easier to do. But our open question for us is, how do we translate these kind of like a spectrum analysis parameters from the Swan into let's say basically into velocities and height of the water into the 3D CFD domain. So that's an open question for us. And if you have some ideas there, I'm very happy to explore that with you, and we can definitely do that. That's something that we are working on with some faculty from UT Arlington, and we hope that very soon we will be able to integrate AdCirc. And particularly if you're interested, please leave a feature request on the forum if you're interested in AdCirc, and if you have any ideas, I would be happy to set up a video call with you, and we can go over how to do that, and I can help you with the coding, and we can probably put it into the HydroUQ together as a user let's say interest in there.
Okay, I have another question. If you gave a disclaimer that the topic today was not on the Tonga tsunami induced by the volcano eruption. Is HydroUQ suited to somebody who is trying to study the effects of that tsunami on the built structures in Tonga?
Right. It's a very unfortunate event, but I mean, I just wanted to put out that disclaimer at the start, just to show that we're not showing any data from the Tonga volcano, because we did not have any of that. We have not done any simulations on that, to be honest. But technically, HydroUQ is equipped to do that. All the HydroUQ is doing, like let's say from a numerical perspective, if I go to look at the higher picture, is that it is essentially trying to see how do I convert these wave inputs into velocity inputs. So it doesn't care where the wave input is coming from. So for example, like you can use GeoClaw. I think Professor Levac has done these simulations on, like, I think there was a recent one that they did, like where you have an asteroid impact onto ocean and how these would generate tsunami waves. So I think they have done these volcano and these kind of asteroid impact and so on, and how these kind of generate tsunami waves. I think there are a lot of examples from GeoClaw side. If somebody would run those things, they can directly bring those things into HydroUQ and should be able to still get the local effects from the CFD using that. I think that should still be possible.
Okay. One other question, which you might have been touched on already, is it possible to model buildings as a simple 3D shape like a cube?
Yeah, absolutely. Let me just go back to the HydroUQ documentation. I mean, I keep going back into documentation when I show things, because it is then easier that you already see that it's already in there. So if we go into the Hydro events and geometry and buildings, right? So if we go into the buildings, we can see, I mean, in the latest version, this is also replaced by a drop-down menu. So you can see different kinds of structures that you can define. If you can just leave the building as a simple cube itself, you don't have to necessarily have an STL file. You can say, here's my cube, here's the length, breadth, and height. I mean, we generally keep it as a cuboid because that gives a generic shape, so people can have different length, breadth, and height. But you can give the same length, breadth, and height can be the same, and then you get a simple cube in there. So it can easily do that, and that's probably the most simplest option available out there. For example, if you look at various papers that have come in coastal engineering as well, in the like where they have looked at a building, I think Professor Andrew Kennedy at Notre Dame recently had this paper that they had a 10 by 10 array, and they were looking at like how the building shielding effects come into picture and so on. there you could see that these all the buildings that they've considered are as cubes, and when you do wave flume experiments, a lot of cubes are considered in there, and this is the most easiest setup that can be done on the HydroUQ. You can just leave the building as a cuboid and then give the length, breadth, and height as the same, and then it's going to automatically construct the STL file. You don't even have to bring an STL, complicated STL file if you don't want to use it.
Okay. Well, I think that wraps up the questions for now. AJ, I want to say thank you very much to you for the presentation. I also want to say thank you for the attendees and for the questions. You can register for additional live expert tips at the SimCenter webpage, which is simcenter.designsafe-ci.org. This concludes today's live expert tips with the NERI SimCenter. We hope you've been inspired to pick up the HydroUQ tool and explore a little bit more about its capabilities and its impact on what you are working on in your research. So again, AJ, thank you very much for joining us all the way from the UK today.
Happy to. And thanks, Matt.